So today we are talking about a new idea, which is velocity versus time graphs. In order to make the jump from position versus time graphs to velocity versus time graphs, we need to remember that on a position versus time graph, the slope tells us the velocity. So that is the main connection here that we need to remember today. So let's review our old relationships: positive linear, negative linear, and no relationship. We're going to remember these position versus time graphs and put them in a velocity versus time graph. So let's take a look at our positive linear relationship. So on our positive linear relationship, we have a positive slope, right? It's increasing on both axes, so it's a positive slope. The positive slope tells us that we have a positive velocity. We are traveling in the positive direction. So for a velocity versus time graph, well, how are we going to set this up? A velocity versus time graph is set up very similar to a position versus time graph, in that we're going to put the velocity on the y-axis and the time on the x-axis. Okay, the reason why I draw it a little bit different though is because we have to account that we might have positive or negative velocities. So we have to have that negative y-axis. So our positive linear position versus time graph, if we translate that into a velocity versus time graph, well, we have a positive constant slope, which tells us that we have a positive constant velocity, right? That slope is constant, it's not changing. So our positive slope is going to be a positive velocity again, and it's going to stay constant, which means that we're going to be on the positive side of this graph. Our velocity is just a constant positive value. Our velocity isn't changing because our slope isn't changing. Okay, so that's how we translate between position versus time to velocity versus time graphs. So let's take a look at our negative linear relationship. For our negative linear relationship, we have a negative slope. Okay, y is decreasing as time increases. So our negative slope tells us we have a negative velocity, and it's a constant slope, so it's going to be a negative constant velocity. So for our velocity versus time graph, we're not in the positive anymore, we're negative, so our velocity is going to be constant and negative. Okay, so our velocity is going to be down here, it's going to be negative and constant. Our velocity isn't changing because our slope isn't changing, and it's negative, so it's going to be on the negative y-axis. So that's how we go back and forth between a negative linear relationship to a velocity versus time graph. If we have no relationships, that means we have no slope. It's a zero slope, so if we have a zero slope, that means we have a zero velocity. So if we translate that to a velocity versus time graph, well, we have a positive side and we have a negative side, but we also have zero, right? Our zero line is our x-axis. So if our velocity is zero, right, because we're not changing position over time, we have a constant zero slope, constant zero velocity. So that's what my velocity versus time graph is going to look like. My velocity is zero because my slope is zero. So that was kind of fast and furious, but we're going to put it into a little bit more context now. And as long as we remember these three relationships, positive linear, negative linear, and no relationship, we're going to remember what our velocity versus time graphs will look like. So next we're going to take a look at what is slope. So we're going to do a really quick overview crash course of slope. So you've calculated slope before in math, but remember slope is designated by the letter m. So if we want to calculate the slope, all we have to do is do rise over run. So that's the difference in two different y values, so y2 minus y1 divided by the run, which is the difference in the x values, so x2 minus x1. Okay, so again, the slope is the rise over the run. So that's going to be really important for us as we move forward. So that rise is the change in y and the run is the change in x. So let's remember that. That's very important. So let's say I have a position versus time graph. Remember, position is on the y and time is on the x. So let's just say it's a position versus time graph for somebody walking. I've got some numbers there for us to be able to calculate the slope. And let's say my graph looks something like this. So the person is starting at 6 meters and they're moving in the positive direction. So all I have to do to calculate slope is pick 2 points. So I'm going to pick the end points. That's something that I always do as a person. I could pick any of those points in between, but I'm just going to pick the end points to work with for my slope. So this point on the end there, that's going to be my second point. So it's my y, or my x2 comma y2. And then the initial condition, or my y-intercept, is going to be my x1, y1 point, my first point. So if I'm going to calculate slope, I need to know what is my y2 and what is my y1. So my y2 is 14 meters. I'm putting the units in because we use units in physics, okay? Minus my y1. My y1 is that y-intercept, which is at 6 meters. So I've got 14 meters minus 6 meters divided by my change in x. So my x2, it is at, well, that's 12, 14, 16. It would be at 16. And what is the unit on the x-axis? It's seconds. So 16 seconds for my time. And then my x1, well, it's right there on the x-axis, or the y-axis, so 0 seconds. Okay, so I'm going to calculate slope here. 14 meters minus 6 meters, that is 8. So I've got 8 meters on the top there, divided by my 16 seconds. And what do we notice here? We notice that those units, meters divided by seconds, that's my unit for velocity. No way, that's why the slope is equal to the velocity. So my slope, which represents my velocity, in this position versus time graph, it's going to be 8 meters divided by 16 seconds, which is 1/2, or 0.5 meters per second. So I just calculated the slope, and now I know the velocity, which is pretty amazing. So the velocity for this moving thing, moving object, moving person is 0.5 meters per second. So that was our crash course on slope. Now let's take a quick look at velocity versus time graphs. How do we translate between the two? So I gave you the stepping stones with our linear relationships, but let's look at a more concrete example, and then we'll do a more complex example later. So let's start out with a position versus time graph. Remember, position is on the y, time is on the x, and then let's just say it's for a moving person. Okay, we'll say that the person starts at the origin, because that's really easy for us. We'll say they start at their origin, at their reference point. They move in the positive direction for a short amount of time, and then they stop there and they pause. So we'll say that they stop with a 0 slope, 0 velocity. Okay, so how are we going to translate this into a velocity versus time graph? How can we make this look like a velocity versus time graph? Well, we are going to evaluate those different segments of motion independently of one another. So there's my velocity versus time graph for the person who's walking. Remember, velocity is on the y-axis and time is on the x-axis. We've got positive, 0, and negative velocity possibilities. And then remember, our slope is equal to our velocity for a position versus time graph. So in my first segment of motion, I have a positive slope, or a positive velocity. Okay, so that means on my velocity versus time graph, during that short amount of time at the beginning, I have a positive constant velocity, right? We did this when we reviewed our relationships in relation to our velocity versus time graph. But what about the second segment of motion? The second segment of motion, I have no slope. I have a 0 slope, which means I have a 0 velocity. So how is that going to translate to our velocity versus time graph? Well, we notice that we have that positive chunk of velocity right there. And then there's kind of an abrupt change. The person's moving and then they're not moving. So at that point, they just stop moving. They stop where they are. How's that going to look on our velocity versus time graph? Well, at that point, they stop moving, so their velocity suddenly becomes 0. So it's going to look kind of like a step function or a piecewise function in math. Okay, so after their positive section of motion, they're going to have a 0 section, right? 0 velocity. But that change happens really abruptly. Okay, so they go from moving to not moving. So there's a really abrupt change in their velocity. So that's why I draw that dotted line, because they go from having a velocity to no velocity. So it just happens instantaneously. So the graph just jumps from a positive velocity to no velocity. Okay, so this was a really quick, I know, fast and furious overview of position versus time to velocity versus time graph, but we have got a video with a little bit more practice for you to see what that translation looks like. So here's that video.